In this lesson, we will learn how to read and interpret phase diagrams, graphs that show how a substance changes state based on temperature and pressure. Thinking back to our lesson on the kinetic theory of matter, we saw that when the particles in a substance gain energy, they move faster and can break free from one another. The amount of thermal energy needed for the particles to break free from one another depends upon the types of intermolecular forces that are present. The stronger the intermolecular force, the more energy that is going to be needed. Thus, water has a much higher boiling point than hydrogen sulfide, H2S, due to the stronger intermolecular forces that are present. Phase diagrams bring these two ideas together. They help us predict whether a substance will be a solid, liquid, or gas at different conditions, and show us special points like the triple point and the critical point. Today we'll walk through what each reason means, what the lines represent, and how to use a phase diagram to answer real questions in chemistry. So here's a phase diagram. There are three main regions we have that are delineated by the different regions. So here's one region, and here's another one, and here's another one. These different lines correspond to where you have a change from a different state of matter. So the way I tell people to figure out what you have for each one is you just imagine that you are making the substance, you're lowering the temperature on the substance, and you are just increasing the pressure. You are just squashing down on it, like trying to make diamonds kind of pressure. And so you say, all right, well, in that case, it's really cold, lots of high pressure. This is going to be the solid. And then you go the other way and you say, all right, well, now I'm going to make it really, really hot, and I'm going to drop the pressure so it's like it's in a total vacuum. In this case, it would be a gas. And then in the part that is in the middle, right in here, would be where you'd have the other remaining phase, which would be a liquid. It's kind of handy that this portion here looks like a cup. So you can just remember that we have a liquid in the cup that's on a phase diagram. So like I said, we also have different phase changes going on. We also have two different special points. We have this first one, which is triple point, and then we have another one. Oh, here's the video for the triple point, sorry. So in this video, we have a flask containing tert-butyl alcohol. It's just a substance that's easy to show what the triple point is. And we're applying a vacuum above it. So this bubbling that you see right now is just due to any dissolved gases that are present being drawn out, as well as the removal of any high energy molecules of tert-butyl alcohol. So after about 30 seconds, all of the gases have been removed, and all of the high energy molecules have also already been removed. And so now it's just getting colder and colder because we removed all of those high energy molecules. And at this point, we can see that we're starting to form a solid. You can tell it's a solid because you can't see through it. But at the same time, we also have the tert-butyl alcohol is starting to bubble. So we have all three states of matter in the same place at the same time: solid, liquid, and gas. All right, so going back to our diagram, we also have this point up here, and it's not because they didn't stop because people get tired of collecting data. The people that make these diagrams, that is their thing to do. They love collecting data. So this is actually the triple point, or not triple point, critical point, and it tells you that this is the point which you can no longer distinguish between the liquid and the gas. So that's why we no longer have a phase change that's evident. So we have some transitions. So if you're going from a liquid to a solid, that would be freezing. Whereas if you go from a solid to a liquid, that would be melting. It's actually solidification and fusion, but people use freezing and melting now. And then for this one, gas to liquid is condensation, And then liquid to gas is vaporization. A lot of people, or a lot of students tell me that it's evaporation. Evaporation is what the substance does below its boiling point. If you're forming a vapor, the gas phase of the substance, it is called vaporization. And then we got our last phase change. So if we're going from gas to solid, most people don't know this one. I usually kind of try to cue my students by saying, all right, so you have probably seen this. This is when you have frost forming from the water vapor that's in the air on window glass and on car windows, and it deposits the frost. So that would be deposition. And going the other way, again, a slightly more familiar term. If you go straight from solid to gas, it is called sublimation. All right, so we're going to go on to actually have some definitions. So critical point, this is the temperature and pressure beyond which you can't tell the liquid from the vapor. I just usually think of it as being the temperature is just so high you can't get it to condense down into a liquid anymore. Triple point, as we saw, that's the temperature at which you have all three states of matter at the same time. The normal boiling point is the temperature at which a liquid will boil or vaporize under 1 atmosphere of external pressure. This is our normal condition. We are normally under 1 atmosphere worth of pressure. So that's how this one has been defined. If you think about if you ever made something like from a box mix, you would know that they often come with high altitude directions. And that's because the temperature at which substances will vaporize or boil decreases as you go to higher altitudes. So if you are trying to boil some water to make some spaghetti and you're living in Denver, which is a mile up, your water is only going to boil at 95 degrees Celsius, not at 100, and it's going to take a lot longer to cook your noodles. So that's something why you need to have these special directions. And then we have normal freezing point, same idea, but it's temperature at which a liquid will freeze under 1 atmosphere of pressure. And then just a reminder, what are the normal boiling and freezing points of water in degrees Celsius? Because sometimes people just get really hung up on that Fahrenheit scale, even though we try not to use that nasty F word in science classes. So hopefully by this point you have recalled that it is 0 degrees Celsius for the freezing point and 100 degrees Celsius for the boiling point. All right, so here is a phase diagram for carbon dioxide. Now it's going to have the same general regions. So we have solid, liquid, and gas. And then we have our triple point right here where they intersect. We have our critical point up there. And it says, why is it not possible to have liquid CO2 at atmospheric pressure? So under our normal condition, 1 atmosphere of pressure. And so you say, well, I go up here to where it's 1 atmosphere of pressure, and I go straight from solid to gas. It will sublime. And that is actually what you see when you have dry ice. Dry ice is solid CO2, and it just sublimes at regular atmospheric pressures. And it does this at a temperature of minus 78 degrees Celsius. So the reason why is because you can't actually have liquid CO2 until you have at least 5.11 atmospheres worth of pressure to keep those nonpolar molecules in close contact with each other. So that's one interesting question that we could answer by looking at phase diagrams. So here we have a comparison between carbon dioxide and water's phase diagrams. And so the question would be, in terms of intermolecular forces, why is water's phase diagram so different from the phase diagram for CO2? And it might look just kind of superficially as though they are the same, because you got the same regions, The only thing that's really different as far as general shape goes is that water has this weird backward slant to it, which means that it melts when you apply pressure to it. But what it is talking about is, why does the behavior at 1 atmosphere pressure? So here we have, for carbon dioxide, it sublimes under 1 atmosphere pressure, and it's at a temperature of -78. And then for water, the temperatures are much higher for the phase changes under 1 atmosphere of pressure. So something else we also, in order to answer that, especially since we're talking about intermolecular forces, we have to think about the Lewis structures. So here we have Lewis structure for carbon dioxide. I'm trying to get my pen to come on. There we go. And so this is completely symmetric. It is nonpolar, which means that it only has London dispersion forces, keeping it in a condensed phase. Remember, London dispersion forces are very, very weak. And then up here, for water, we have hydrogen chemically bonded to oxygen. This is an asymmetric molecule, so that means it is going to be hydrogen bonding. I'm not used to this pen yet. So the answer would be, the reason why the phase diagrams are so different is because there is such a difference in the intermolecular forces. Carbon dioxide has only London dispersion forces, so there's very little keeping it together in a condensed phase. Whereas hydrogen bonding, we have lots and lots of the intermolecular hydrogen bonds helping to keep those water molecules stuck to each other. And so it has higher boiling points, higher melting points. It wants to stay in that condensed phase. And I do believe that is it. So thank you for joining me.